Hi, in this video I'm going to present several arguments from physics that support the idea that causality is an illusion. And this is kind of a new twist on an old argument. You often hear arguments that free will is an illusion because everything is caused. I'm going to argue that causality is an illusion. This kind of leaves open the question of free will. I'll have more to say about that in later videos. So let's move on. So here's a brief outline of what I'm going to talk about. First, I'm going to define what I mean by illusion, and I'll give an example that hopefully will make this clear. And I'll talk about what I mean by causality and define that precisely. Then I'll give reasons why I believe causality is an illusion. I'm going to give several examples from physics: time reversibility, least action principle, quantum entanglement, and imaginary time. And I'll try to give explanations that are not too technical, but are rigorous enough to be accurate. And then, if not causality, then what? And I'll talk about that at length in my next presentation. Okay, so let's begin. What do I mean by illusion? It's not that it's not real, it's just not as fundamental as it appears to be. And I think the best way for me to explain this is to use an example. Consider friction. Friction has enormous practical importance. If you've ever tried to walk down the street during an ice storm, you'll realize that without friction we couldn't walk. Couldn't drive a car, couldn't tie your shoe, wouldn't have clothes. Friction really runs our lives. At one time, friction was thought to be a fundamental principle of the universe. The Greeks thought that if you push an object, it will stop moving naturally. The Greeks also thought that heavier objects fall faster than lighter objects. Now we know this is because of air resistance, which is a type of friction. The Greeks thought these things were fundamental. Now we no longer think of these as fundamental. Modern physics explains friction in terms of other more basic concepts. Friction is a secondary or derived phenomenon and not a primary one. That's the claim I'm making for causality. It's not as fundamental as it appears to be. Cause and effect does not run the universe the way it seems. Now, what do I mean by causality? We all have the idea that every occurrence can be explained as a consequence of previous events, and so on. The previous events can be explained by events prior to that, and so on, stretching back to the Big Bang. Now, in physics jargon, the idea of causality can be expressed as follows: that time is the basic dynamical variable, that is, that reality unfolds as time progresses. In a more mathematical way, we can say that the equations that determine reality have time as an independent variable. If you're not mathematical, you can think of this idea that reality unfolds as time progresses, just like a flower unfolds over time. Now, causality is such a universal notion, I think it's worth taking a moment to consider the question: is causality really logically necessary? In fact, in many scientific and philosophical arguments, causality just goes without saying. For instance, there's St. Augustine's famous argument for the existence of God. He says that everything we see has a cause, and those causes have causes, and so on down the line. There's a chain of causation, and it must end with a first cause that's not caused. And he calls that cause God. On the other side of the atheism debate, there's Sam Harris, who says that causality shows that free will does not exist. Every thought that we have is preceded by an impulse, which causes the thought. He also points to experiments that show that the brain shows that the decision is made even before you're conscious of making the decision. Now, I would like to point out that these conclusions are based on everyday experience, but unexamined assumptions are very dangerous. Everybody knows that the speed at which your clock moves doesn't depend on how high you are. That someone who lives in Colorado on top of the mountains has the same rate of time as someone who lives in Death Valley. Einstein comes along and tells us, no, that's not true. Everybody knows that an object's length does not change if it moves. Einstein comes along and says, no, that's not true. It's not just that the object appears to be not as long. It is physically not as long if it's moving relative to you. Everybody knows what it means for two events to be simultaneous. Einstein comes along and says, no, you don't. Everybody knows that a particle, if it's faced with an energy barrier that's too high, it can't pass that energy barrier. Quantum mechanics comes along and says, that's not true. And that's fortunate for us because otherwise you wouldn't be using the computer that you're using now. So I just wanted to point out that the fact that causality seems so obvious is no argument for saying that it's a fundamental fact of reality. Just the same as with friction. We need to examine these assumptions. So let me give some reasons why I think causality might very well be an illusion. So if you go to the equations of physics, there's nothing special about forward time. We said that causality means that reality unfolds as time progresses. But if you look at the equations of physics, there's nothing that distinguishes forward time from backward time, or from for that matter, from any other physical dimension. Now, classical mechanics is time reversible. The equations of mechanics can run forward and backward. If you take a movie and run it backwards, that's showing a physically possible process. Of course, it's unusual for a stone to jump out of the water back into somebody's hand, but according to the physical equations, it's possible. The fact that doesn't happen has nothing to do with the classical equations of motion. Okay? In relativity, time is just another dimension in the space-time continuum. There's nothing special about it. It's just another dimension. In fact, if you go to electromagnetism, there is a formulation of electromagnetism where particles in the past and particles in the future are on equal footing. A charged particle's influence on particles in the future is exactly symmetric with the particle in the future's influence on the particle in the past. And this is called Wheeler-Feynman electrodynamics, and it's been shown to be mathematically equivalent to the electrodynamics that's usually used. There's no reason to prefer one over the other. There's a similar version of time-symmetric quantum mechanics called transactional quantum mechanics. And in quantum field theory, the Feynman propagator is also time-symmetric. You may have heard about antiparticles being equivalent to particles traveling backwards in time. So there's no distinction between forward time and backward time. We could think of the particles that we know and love as antiparticles traveling backwards in backwards time. Okay, so there's nothing special about forward time in physics. Now, this next reason is a dirty little secret that all physicists know, but they tend not to talk about it. I'm not really sure why. But there's a principle in physics called the least action principle, a very fundamental principle that occurs in classical and quantum mechanics. And this principle, well, let me give some background here. Physical equations are typically derived on the basis of an underlying process. For example, the shape of a hanging cable minimizes gravitational potential energy. So if you take a cable and you decide to hang it between 2 points, point A and point B, say, the shape that cable takes is determined by minimizing the gravitational potential energy. When you first hang it up, it may not take that shape, but after a process of minimization, it ends up in the shape that will minimize the gravitational potential energy. Now, the least action principle says that the path that a particle takes from space-time point A to space-time point B minimizes the action over all possible paths from A to B. So there's at least a surface similarity between these two situations of hanging a cable between 2 points and the path that a particle travels between 2 points. Now, I'm not going to say what the action is. Suffice it to say that it's something that's calculated on the basis of the path from A to B. Now, I want you to notice here that the points A and B here are not points in space, they're points in space-time. So, for instance, the point A may represent a spatial position at time 0, and the point B may represent a spatial position at time 5 seconds, for instance. And it turns out that if a particle travels from this position A at time 0 to this position B at time 5, the path that that particle takes will minimize the action over all possible paths from A to B. I talk about particles here because from the modern physical picture, any physical motion can be broken down into the motion of particles, whether they're matter particles or photons or neutrinos or whatever type of particles or gravitons. Okay. So if we run this analogy to its what seems to be logical, if this minimization principle, the least action principle, corresponds to a process of minimization, then it must know that the particle, where the particle is going before it gets there. For this least action principle to correspond to a physical process or mechanism, that must be the case. So I think that went by a little bit quickly. Let me give an example here. All right, so here's what I was talking about. If I have a hanging cable, and this A represents a point in space, here I have the horizontal direction, separation, and here I have the height. So I have two different points at different heights that are separated from each other, and I hang a cable between them, and that cable will take a shape, as I said, that minimizes the gravitational potential energy. Okay. On the other hand, if you have a traveling particle, here, this dimension here is no longer spatial separation. I take this as representing time. So time along this axis, and here is distance. So here I'm picturing a one-dimensional universe. I can't picture more on a two-dimensional sheet of paper. And here I have a space-time point A, which is prior to this space-time point B, because the time is less. They're separated by a certain distance. And it turns out, I know that there's a particle traveling from point A to point B. And it turns out that the path that the particle travels will minimize a certain quantity called the action. Okay, so as here, this shape of this cable is determined based on fixing point A and point B. If the least action principle represents a physical process, then the points A and the point B must be fixed before the intermediate motion is determined. Okay? But that's completely against causality. We say that the particle travels as it goes and decides where it goes as it goes, and it doesn't know where it's going to end up. So you might ask, why don't physicists pay more attention to this? Why isn't this fact publicized in popular science journals? Well, the reason is that the least action principle is usually presented as a mathematical convenience. It's an elegant, coordinate-free characterization of Newton's equations. In other words, Newton's equations are fundamental, and the least action principle is an elegant way to formulate them that doesn't depend on the coordinates that you're expressing the equations in, so it's easier to solve equations mathematically. And it gives rise to some very elegant equations called Hamilton's equations. However, there's a problem with this point of view. The point is that quantum mechanics is not derived from Newton's equations, but from Hamilton's. And Hamilton's equations are based on the least action principle. So it seems somehow that the least action principle is more fundamental than Newton's equations. In quantum field theory, the least action principle is often the only way to derive the field equations. So here again, we have the idea that the least action principle, which depends on the past and the future determining the motion of the system, seems to be fundamental. Okay. So I summarize that if the least action principle actually does represent the outcome of a process, then the past and the future influence what happens in between. And that shoots a hole beneath the waterline of causality. Causality is not compatible with that point of view.